When you click send on an email or type a URL into your browser, your data doesn't just magically teleport across the world to the destination server. Before a single bit can travel across copper cables, fiber optic glass, or Wi Fi, your raw application data must be wrapped, addressed, and converted through a precise multi layer assembly line. In the early days of networking, proprietary standards ruled. An IBM mainframe could not talk to a DEC machine, locking companies into isolated hardware silos. To solve this chaos, open standards were created: the theoretical 7-layer OSI reference model and the practical 4-layer TCP IP model that runs the internet today. In this episode, we will deconstruct the 7 layers of OSI, map them to the 4 layers of TCP IP, identify their protocol data units, and trace the entire encapsulation engine step by step.
The Open Systems Interconnection, or OSI model, was developed by the ISO as a 7-layer theoretical blueprint to standardize how network protocols interact. Let's build both models side by side on our architectural canvas, layer by layer. At the very top sits OSI Layer 7, the application layer. This is not the software application itself like Chrome or Outlook, but the network-aware protocol interface that services your applications, such as HTTP and HTTPS for web traffic, DNS for domain lookups, and SSH for secure command line access. Right below it is OSI Layer 6, the presentation layer. Layer 6 acts as the universal translator and security checkpoint. It formats raw data into standard syntax like JSON or ASCII, compresses payloads to save bandwidth, and performs data encryption and decryption via TLS/SSL. Next is OSI Layer 5, the session layer. Layer 5 establishes, maintains, synchronizes, and terminates active dialogue sessions between two network applications, ensuring that if a connection drops temporarily, the session can resume without restarting the entire data stream. Now, look at the TCP IP model on the right. The engineers who built TCP IP realized that application logic, formatting, and session management are all handled directly inside the software itself. Therefore, TCP IP consolidates OSI layers 7, 6, and 5 into a single unified top layer, the TCP IP application layer. Moving down to layer 4 in both models, the transport layer. This layer handles host-to-host end-to-end communication, session segmentation, and port numbering. It chooses between TCP for reliable, ordered, error-check delivery via three-way handshakes, or UDP for fast, lightweight, connectionless streaming. Next is OSI Layer 3, the network layer, mapped to the internet layer in TCP IP. This layer is responsible for logical addressing using IPv4 or IPv6 and path determination across multi-router networks. Routers operate at this layer, inspecting destination IP addresses in routing tables to forward packets across the global internet. Beneath the network layer is OSI Layer 2, the data link layer. Layer 2 is responsible for node-to-node hop delivery on the local network segment. It handles physical 48-bit MAC addresses, frames data packets, detects transmission errors using a frame check sequence, and is the home of Layer 2 switches and VLANs. At the foundation is OSI Layer 1, the physical layer. This layer defines the physical and electrical specifications of the network, converting structured frames into raw binary bits, zeros and ones, transmitted as electrical voltage on copper wires, pulses of light in fiber optics, or radio waves in the air. Just as it did for the upper layers, the TCP IP model consolidates OSI layers 2 and 1 into a single foundation layer called the network access or link layer. To easily remember the 7 OSI layers from bottom to top for your CCNA exam, use the classic mnemonic: please do not throw sausage pizza away. Now that we know the layers, how does data actually travel between them? At each layer, data is packaged into a specific format known as a Protocol Data Unit, or PDU. Think of encapsulation like nesting Russian dolls or placing a letter into progressively larger shipping containers. The process starts at the top. The application layer creates the raw payload, such as an HTTP GET request or an email message. At layers 7, 6, and 5, the PDU is simply called data. When the data reaches the transport layer, layer 4, the operating system adds a layer 4 header containing source and destination port numbers, sequence tracking numbers, and TCP control flags. This combined unit is our layer 4 PDU, the segment, or datagram if using UDP. Next, the segment moves down to the network layer, layer 3. Here, an IP header is prepended, containing the source IP address of the sender and the destination IP address of the target server. This layer 3 PDU is called the packet. The packet descends to the data link layer, layer 2. Layer 2 is unique. It attaches an Ethernet header at the front with source and destination MAC addresses and appends a trailer at the back containing a frame check sequence, FCS, to detect transmission errors. This complete unit is the layer 2 PDU, the frame. Finally, the physical layer, layer 1, encodes the entire frame into raw binary ones and zeros, converting the bits into electrical voltages, light pulses, or radio signals across the physical medium. At layer 1, the PDU is bits. When the bits arrive at host B, the entire process runs in reverse, decapsulation. Layer 1 reconstructs the frame and passes it to Layer 2. Layer 2 recalculates the frame check sequence. If the math matches with 0 errors, it strips off the MAC header and trailer, handing the clean packet up to Layer 3. Layer 3 on host B inspects the destination IP address. Confirming the packet is meant for this machine, it strips off the IP header and passes the inner segment up to Layer 4. Layer 4 examines the destination port number, port 443, identifies the target application as the HTTPS web server service provider, strips off the TCP header, and delivers the original raw data payload directly to the web server process. To ace your CCNA exam questions on PDUs, memorize this exact mapping. Layer 7 is data, Layer 4 is segment, Layer 3 is packet, Layer 2 is frame, and Layer 1 is bits.
Understanding encapsulation theoretically is one thing, but how does it behave across real hardware, like switches and routers? Let's trace a packet hop by hop across a multi-segment network to reveal the #1 trap on the CCNA exam. Host A wants to send data to host B on a remote subnet. Host A builds the layer 3 packet with source IP 192.168.1.10 and destination IP 172.16.1.100. But because the destination is on a different network, host A sets the destination MAC to its default gateway, router 1. When switch 1 receives the frame, what does it do? As a layer 2 device, switch 1 only looks at the layer 2 MAC header. It forwards the frame toward router 1 without altering a single bit in the MAC, IP, or TCP headers. When router 1 receives the frame on interface G0/0, it strips off the layer 2 header and trailer. It checks the IP header, decrements the time to live, or TTL, by 1, inspects its routing table, and determines the packet must exit out interface G0/1 toward router 2.
Now, here is the golden rule for your CCNA exam. IP addresses remain unchanged end to end, but MAC addresses are rewritten at every single layer 3 hop. Router 1 re-encapsulates the packet with a brand new layer 2 frame. Source MAC becomes router 1's egress interface, and destination MAC becomes router 2's ingress interface. Router 2 repeats the exact same procedure, strips the old layer 2 header, decrements the TTL from 63 to 62, and encapsulates the packet into a final local frame with source MAC of router 2 and destination MAC of host B. Host B decapsulates the frame, validates the IP, delivers the payload to the web server process, and prepares its response, proving that encapsulation is the engine of the entire internet. Watch out for these 3 classic Cisco CCNA exam traps. First, switches never change IP or MAC addresses. Second, routers always decrement TTL and rewrite layer 2 headers. And third, never mix up your PDUs. Data at layers 7 through 5, segment at layer 4, packet at layer 3, frame at layer 2, and bits at layer 1.
In summary, the OSI model provides the theoretical 7-layer framework, while the 4-layer TCP/IP suite drives real-world network communications. As data moves down the stack, encapsulation wraps your raw payload into a segment at layer 4, a packet at layer 3, a frame at layer 2, and converts it into raw physical bits at layer 1. Now that you understand how data is formatted and addressed,
Who actually moves these packets across enterprise networks? Make sure to subscribe and hit the notification bell so you don't miss episode 02, where we break down modern network hardware, from core routers and layer 3 switches to next-gen firewalls, wireless controllers, and Cisco Catalyst Center.